I want you to just try and visualize something for a second. Imagine a library,
Okay.
but not just any library, not
Yeah.
your local branch. Imagine a library that contains every single biomedical research paper ever written.
That would be a structure that would dwarf the Library of Congress easily.
It's massive. We're talking about over 34 million abstracts just in PubMed alone. And here's the kicker.
Mm.
Every single day, thousands more get added to the pile. So put yourself in the shoes of a doctor or a researcher, right, where you're trying to find a cure. How do you find the answer? Hiding in a stack of paper that's graying faster than you can possibly read it.
You don't. You just can't. It's physically impossible for any one person to read, let alone synthesize that amount of information.
Right.
And this creates a fundamental tension in modern science. We are drowning in information, but we're starving for wisdom. We have the data, but we lack the causal understanding of how it all connects.
That distinction right there between just having a mountain of data and actually understanding cause and effect, that's really the theme of this whole deep dive.
It is.
We got two really heavy-hitting pieces of research on the table today.
We do. On one side, we have this breakthrough in artificial intelligence called iKraph.
That's IKRAPH.
Right, iKraph. And it's essentially trying to read that infinite library to find hidden cures.
And on the other side?
On the other side, we have a study, this one from Nature Aging, that just completely reframes how we measure getting older. It moves us away from just counting birthdays to understanding the biological causes of aging.
And the thread tying them both together is causality.
Exactly. It's the big shift from saying these two things happen at the same time to this thing causes that thing. It's a huge leap.
Okay, so let's start with that external problem, the data monster.
Hmm.
I was looking at the iKraph documentation from Insilicom, and the sheer volume it's dizzying. They pulled over 10 million unique entities, 30 million relationships.
Yes.
But let me play devil's advocate for a second. Isn't that just a fancy search engine? I mean, Google Scholar already scans millions of papers.
Not quite. It's a really good question, but the function is different. Google retrieves documents based on keywords. You type in aspirin, it gives you a bag of words that contains aspirin.
Okay.
iKraph builds what's called a knowledge graph. Think of it less like a list and more like a massive conspiracy wall.
Ah, like in the detective movies, with the thumbtacks and the red string connecting everything.
That's the perfect image. So the nodes are the thumbtacks.
A gene, a drug, a disease.
Right. And the edge, the string connecting them, that's the relationship.
Yeah.
But here's where iKraph does something critical, something different. Most older systems just looked for co-occurrence.
Meaning if aspirin and headache show up in the same sentence, it draws a line.
Exactly.
Which seems risky, doesn't it?
Yeah.
Because the sentence could say aspirin causes headaches or aspirin cures headaches if you don't know the difference.
You're in a lot of trouble. I mean, if you're trying to develop a drug, that distinction it's fatal. iKraph uses what's called a causal knowledge graph. It actually predicts the direction of the relationship. It knows drug A inhibits gene B. It understands the verb, not just that the words are close to each other.
The source material mentions something called PSR, Probabilistic Semantic Reasoning. That sounds fancy. But my takeaway was that it lets the AI make leaps that a human might miss.
It allows for transitive reasoning. And this is the real superpower here. Let's say you have 3 separate papers. Paper number 1 says, drug X activates protein Y.
Okay.
Paper 2 says nothing about drug X, but it says protein Y blocks disease Z.
And a human researcher might never read both of those papers. They're in different journals, maybe published years apart.
Yeah.
The connection is just lost.
Precisely. But the AI sees both of those strings on the wall. It infers that if X activates Y and Y blocks Z, well, then drug X might be a treatment for disease Z.
It's finding the hypothesis that hasn't even been written yet.
Yes, it's doing logic puzzles at a scale of 34 million documents.
But does it actually work? I mean, logic in a computer is one thing. Biology is messy.
So they ran a retrospective study on COVID-19 to prove it. They fed the system data from really early in the pandemic, so March 2020 through May 2023.
I saw this. This was tied into that Litcoin challenge from the NIH, wasn't it?
Part of it, yes. And that team actually won first place in that challenge, which proved their extraction accuracy matches human experts.
Wow.
But for the COVID study, the results were just striking. In the first 4 months of the pandemic, while everyone was scrambling, iKraph identified around 1,200 candidate drugs, just by reading.
Okay, but identifying them is one thing. Were they any good? Were they the right drugs?
That's the key validation step. 1/3 of the drugs it flagged in just those first 2 months were later supported by actual clinical trials or publications.
1/3. That seems incredibly high for drug discovery. Finding a viable drug target is usually like finding a needle in a haystack.
It's a massive hit rate. It allows for, effectively, real-time drug repurposing. Instead of waiting 5 years for some manual review, you're generating high-quality leads in minutes. They did it for cystic fibrosis, too, and got a recall of 63%.
So it found 63% of the known drugs just by analyzing the text.
Yeah.
Okay, so we have this AI, iKraph, solving this huge external data problem. It's mapping the world's papers to find causes. Now I want to pivot to the internal data problem, mapping what's happening inside our own bodies.
Which brings us to the second paper. And this one tackles a really major flaw in what we call epigenetic clocks.
We should probably define that for people who aren't, biohackers. We're basically talking about looking at your DNA to see how old you are, biologically.
Exactly. You have your chronological age, the candles on your cake, but your biological age is measured by looking at something called DNA methylation.
Right, methylation.
Think of methylation like little dimmer switches attached to your genes. As you get older, some switches get turned up, some get turned down.
And for the last decade, the assumption has been pretty simple. If the switches change, you're aging, and aging is bad. So any change on the clock is a sign of decline.
Correct. Traditional clocks, like the famous Horvath clock, they look at all these changes and just give you a single number. If your methylation pattern looks like the average 50-year-old's, then you are biologically 50.
But these researchers realized something critical.
They realized correlation isn't causation.
So they're saying that just because a dimmer switch moves, it doesn't automatically mean the body is breaking down.
Exactly. I mean, think about it. As you get older, 2 things are happening. 1, you accumulate damage, just wear and tear. 2, your body tries to fix that damage. It adapts. It activates defense mechanisms.
Okay, I think I see where this is going. If my body's working overtime to repair itself, my methylation changes to help with those repairs.
Yes.
And a traditional clock just sees that change and says, uh-oh, lots of activity here. You're aging really fast.
Yeah. When actually you might be fighting back effectively. The old clocks conflate the fire with the firefighters. They just see the commotion and assume it's all destruction.
So how on earth did they untangle that?
Yeah.
Looking at a DNA sample, how do you know which change is damage and which one is actually repair?
They used a technique called Mendelian randomization. It's complex statistics, but you can think of it as nature's own randomized controlled trial.
A natural experiment.
Exactly. They analyzed over 420,000 DNA sites, these CPG sites, to see which specific changes actually caused higher mortality, and which were just bystanders or even protective.
And from that huge analysis, they built 3 totally new clocks.
They did. Causage, damage, and adaptage.
Okay, break those down.
Causage is the general causal clock, but the important ones are the other 2. Damage, that's DAM, measures pure destructive aging. If this number goes up, your risk of death goes up. It's the rust on the car.
And adaptage.
Adaptage tracks the protective changes, and this is the real game changer. A high adaptage score is associated with lower mortality.
Wait, that completely flips the quantified self idea on its head?
It does.
You could have 2 people who both look old to a traditional clock.
Right.
Their methylation is different from a 20-year-old's, but one is just full of rust high damage, and the other is full of, reinforced steel high adaptage.
Precisely. The researchers use that car analogy, and it's a really good one. Over time, a car gets dense in rust. That's damage. But a smart owner might also install a better radiator or deeper tire treads to handle rough roads. That's adaptage.
And the old school mechanic, the old clocks, would just look at the car and say, well, it's not factory new, it's changed, it's old.
Yep.
But the difference is life or death. If I try to reverse aging blindly, if I try to reset my whole system back to factory setting.
You might be scrubbing off the rust, but you might also be ripping out that new radiator you install.
Have we been doing that? Have we been accidentally suppressing our body's own best defense mechanisms in the name of anti-aging?
It's a very real possibility. I mean, if you suppress a methylation change that was actually a protective adaptation, you might make someone look younger on paper, but you've made them more vulnerable in reality.
The study actually put these new clocks to the test, right? To prove this distinction matters.
They did.
Let's talk about the stem cell case study. This is the iPSC reprogramming, taking an old cell and forcing it all the way back to a baby state.
Yes, exactly. It's considered the gold standard of rejuvenation in a lab setting. And when they applied these new clocks, damage dropped significantly. The rust was gone.
Okay, that's what we'd expect.
Yeah.
That's what we want.
Adaptage actually increased.
Hold on. So the cells got older on the adaptation scale as they got younger on the damage scale?
In a way, yes. As the cells were clearing out the damage, they seemed to enter a sort of hyper-adapted state. They kept their protective mechanisms turned on.
So a traditional clock would be confused by that.
It would. The signals would cancel each other out, low damage, plus high adaptation might just look like medium age. But with the new clocks, you see the truth. Damage is gone, protection is high.
It's like they kept the wisdom but lost the wrinkles.
Yeah.
That is fascinating.
It suggests that true rejuvenation isn't just erasing time. It's about erasing damage while preserving or maybe even boosting adaptation.
Now compare that to something purely destructive, like smoking.
Right.
I'm assuming smoking just tanks everything.
It pretty much does. Smokers showed a massive acceleration in damage. Cigarettes are basically liquid rust for your biology.
Did their bodies try to adapt at all? Did adaptage go up?
It tried, but not nearly enough. The damage just overwhelmed the system. But they saw an even starker version of this with sun exposure. They looked at skin samples, sun-exposed versus protected skin.
Sun exposure ages skin, everyone knows that. So damage shot up.
Massive spikes in damage, yes. But here's the really interesting part. Adaptage actually decreased.
It went down. So the sun didn't just damage the skin, it actually broke the repair shop.
That's the hypothesis. The stress was so high that the body's adaptive mechanisms couldn't keep up, or maybe they were themselves damaged. The radiator couldn't be installed fast enough.
This level of nuance is incredible. It starts to explain why some things kill us and some things, make us stronger. Speaking of which, there was a positive finding in there. Omega-3s.
Yes, finally some good news. A 6-week study of omega-3 supplementation.
And?
The results showed a reduction in damage and an increase in adaptage.
Okay, that sounds like the holy grail. You're lowering the rust and upgrading the engine at the same time.
It's a very, very promising signal, and it shows that we can finally measure if an intervention is working the way we want it to. Before, if a treatment changed your methylation, we didn't know if it was hurting or helping. Now we can see the split.
There was one other kind of weird finding in the notes that I really want to touch on. The babies born small for gestational age, SGA.
Ah, yes, the SGA babies.
Mm.
These are infants born smaller than they should be, usually because of some kind of nutrient limit in the womb.
And the clock showed something totally unexpected.
They did. You might think these babies would be developmentally delayed or damaged because they lacked resources, but the clock showed they had lower damage and higher adaptage.
So being small wasn't a failure. It was a strategy.
That's a perfect way to put it. The fetus likely sensed a low-nutrient environment and sort of aged its adaptation systems to survive. It developed a protective mechanism staying small to conserve energy.
Wow.
It's a perfect example of why biological age isn't just one number. That high adaptage is likely why they survive, even if it looks like aging on a simple graph.
It recontextualizes the whole idea of stress. Some stress builds adaptage, some stress builds damage. And knowing the difference is, well, it's everything.
And it connects right back to that core mission we started with, replacing big data with smart data.
Right. iKraph stops us from just drowning in papers and starts giving us actual causal hypotheses. Drug A causes a cure for disease B.
And damage and adaptage do the same thing for our own bodies. We can stop looking at aging as this one single thing. We can finally start asking what causes the decline and what causes our resilience.
It really reframes the future of medicine then. Instead of trying to be 20 years old forever, maybe the real goal is to be a hyper-adapted 80-year-old, someone who has all the protective changes of time without the accumulated damage.
Which raises a really provocative question for the next decade of research. If we can specifically measure adaptage, could we develop treatments that don't just repair damage, but that actually, artificially induce those protective adaptations?
Like a vaccine for aging.
In a sense, yeah. Could we vaccinate ourselves against aging by boosting adaptage before the damage even occurs, pre-adapting the body to the stress of time?
Pre-adapting to time. I love that concept. It's not about turning back the clock anymore. It's about building a better clock.
Precisely. And for the first time, we actually have the tools, both the AI to find the mechanisms in the literature and the biomarkers to measure the results in our cells to actually try.
Well, that gives me a lot to think about. I think I'm going to go check my rust levels and maybe take some omega-3s. Thanks for guiding us through the stack today.
It was a pleasure.
And to you, the listener, thanks for diving deep with us. Take care of your adaptations, and we'll see you next time.